This lesson deals with additional SPICE testing of the 555 timer and also some additional applications of the 555 timer. You can find these notes in the ECE402 ebook in Chapter 7 starting on page 24. One of the specs we looked at in the datasheet was called sinking current. This occurs when the output of the timer goes low. So can we force that to happen? So if I take the trigger and hook it up to VCC, then this is greater than 1/3 VCC. And so the output of the trigger comparator is a logical 0, which is the set line. And if I tie the threshold to VCC, that's greater than 2/3 VCC. So the output of that comparator is going to be a logical 1, which is the reset line, and the output will go low. Put a battery here, same as the 15 volts, and then put a resistor here. If this was 0 volts back to ground, I would have 15 volts divided by 300 ohms. That'd be about 50 milliamps. So let's see what happens. My output voltage is about half a volt, and the current's about 48.328 milliamps. Let's go back into the data sheet on page 124, and let's see what the spec is for output voltage low. This is page 124. So here's the output voltage low. If you're sinking about 50 milliamps of current, the voltage should be about 0.4, maximum of 0.5. That's pretty close to what we had. We had 0.5 volts, and we had 48 milliamps. So our model does predict the sinking of current. Let's next take a look at sourcing current. In this case, the output has to go high. If I had a 15 volt power supply and this went to 15 volts, if I put 150 ohms here, I get about 100 milliamps. How can I force the output to go high? Let's play the same trick. Let's tie this threshold and trigger to a value that would make it go high. If I tie the trigger to 0 volts, that's less than 1/3 VCC, so we're going to get a logical 1 out of the trigger comparator, which goes to the set line. And if this is less than 2/3 VCC, which is equal to 0, then the threshold comparator will get a logical 0, which is the reset line. So we'll set the output high. See what we get. So node voltage 3 is 13.39 volts, and the current's about 89.286 milliamps. Pretty much close to what I expected. If this was 15 volts, this would be 100 milliamps. Let's go into the data sheet and see what the spec is for a similar set of test conditions. And so again, let's go back to page 124 and let's find the case where the output's high and we're sourcing about 100 milliamps of current. So here's again page 124, the output's high and we're sourcing about 100 milliamps of current. We would expect to get 13.3 volts. Pretty close to what we would expect from the data sheet. So the model's predicting what should happen. We saw in the datasheet that there were some specifications about propagation delay. Let's look up our monostable that we had before, and let's change the capacitor and make it about a factor of 10 smaller. It was 0.01 microfarads before. I'm going to make the load here an open circuit with a 100 picofarad capacitance here, and that would kind of mimic my oscilloscope. So I can take a measurement on my scope and roughly see if I get roughly the same results. I made my pulse a little bit narrower. Here it's going to be just 0.1 microseconds wide with a rise and fall time of 1 nanosecond. That's also going to be my print step here. So let's see what happens. Here's my trigger pulse, very narrow. And then here's the voltage across the capacitor. Now when this drops below 1/3 VCC, we see that the output begins to shoot up, a little overshoot and ringing. And the time delay was about 300 nanoseconds, more precisely 293 nanoseconds. Now in the data sheet it said that the rise time was on the order of 100 nanoseconds, so this is much faster than the data sheet. And the time delay is about 300 nanoseconds, and the data sheet says about 100 nanoseconds with. So we're in the ballpark on these numbers. And again, there's an overshoot and ringing here that, again, I didn't think belonged there, but when you look at it on a fast scope, you can see it. Then this thing times out in 16.3 microseconds. That should be in 15 microseconds. Part of the problem here is actually the time it takes when the output goes high to eventually send a signal back to the discharge transistor. And you can see here, there's about a 1 microsecond delay before the capacitor begins to charge. This is basically taking that transistor and going from saturation to cutoff. So there's a time delay with any transistor when you try to switch it. And so some of that error for here is actually coming from that delay. That's actually not in the data sheet, but if you do take measurements on these, you'll see that indeed there is a delay there. Let's take a look at the current that's coming out of the power supply. And you can see there's different things happening here. When the output's low, we're getting about 14.5 milliamps, and we had said before that the current taken in by the chip was largest when the output was low. And you can see when the output's high here, it's actually less. Similar to the data sheet, but again, not exact. But there's something funny happening right here, this big spike. So what's going on? Let's go back and look at the schematic again. So here I've got a transistor here, Q22 and Q24. And normally when this one saturates, this one's cut off. And then when this one is actually cut off, this one is basically going active. Now when you're switching between this going from being a short to an open, it's possible for both of these transistors to be on at the same time. In other words, just for a small instant in time. When that occurs, we're basically seeing a big tug on current from the power supply. There's a spike here about 343 milliamps. This was one of the things people noticed after the 555 timer was released. They eventually made some changes to this output stage and got rid of this spike. But in the interim, they recommended putting a capacitor across the power supply pin to ground. What would happen is that when you needed to spike a current like this, instead of pulling it from your power supply, which might be several inches to feet away, you could draw that current from a large capacitor in parallel with the power supply. Let's go back to our astable again and see what the effects of propagation delay are. Again, I need to speed things up, so I'm going to change my capacitor from 0.01 microfarads to 500 picofarads. And again, have a load here just in the oscilloscope so I can verify this experimentally. And again, I'm going to delay them starting with power supply. Let's take a look at what happens. So you can see here there's a little delay. After we trigger it, output goes high, comes back down, a longer interval, then a shorter one, and then a similar size one. Pretty much have like a square wave. A little bit of a time delay back through the chip before the discharge transistor is released, charging up, charging down, and so on. My trip point should be 2/3 VCC or 10 volts. You can see there's a little bit of a time delay of about 500 nanoseconds before my output starts to drop. And again, my fall time and rise time are pretty fast here compared to the data sheet. And they would be expecting time delays in here, but what was given in the data sheet was for a monostable. Then we come back and this discharges down to 5 volts. There's a time delay before the output starts to change, and that's about 622 nanoseconds. And then there's again a delay time about 1.3 microseconds before the discharge transistor is gone from saturation to cutoff. So we're seeing the effects of the non-ideal timer with the full chip simulation, and my measured results were pretty close for the time delays, but my rise and fall time were nowhere near as fast as they are in the simulation. So not a big factor, but the time delay, getting that sort of in the ballpark would be more significant. I could play again with the parameters of the transistors, but the main thing I don't know about the transistors inside the chip is the actual size of the transistors. The size determines the overall capacitance, but the model's pretty close. Here I would expect to have a frequency of about 35 kilohertz by taking our formula for the period. The actual measured here is about 31.481 microseconds for the period, and a corresponding frequency of about 31 kilohertz. Effects of the non-ideal timer are clearly slowing things down, not happening as fast as we would expect them to. I did one more test on this astable circuit by toggling the reset pin from high to low after about a 50 microsecond delay. So let's see what happens. So when the reset pin is high, we have our astable like we had before. And then here I actually brought it down to 0 volts, and once I crossed about 0.7, things start to change. And you can see here the output starts to fall and it comes back down again. There's a delay of about almost 2 microseconds. But once you activate the reset pin, pretty much the capacitor will discharge. This will all go back to 0. Now there aren't any specifications in the data sheet for this, so again I try to measure this to see what it would look like. So my lab measurements and my simulation are fairly close, except on the rise time and the fall time are a little bit faster in the simulation than what I'm seeing in lab. Let's take a look at an application. This is a capacitance meter that uses a DC voltmeter to convert a capacitance to a DC voltage. Take a look at the left side of this circuit. This is an astable. We can calculate the output of this, but it also has something special here. It's called a pull-up resistor. What this is going to do is lift this output up to the power supply, just like we did with the comparator circuit. So you can figure out what this is going to do. Now, the value of this resistor is much, much smaller than this one. If you recall from our discussion of the A-stable, that's going to give us a very narrow pulse. And with the values here times the natural log of 2, we're looking at about 70 microseconds for this interval. And the period that's here is going to be equal to natural log of 2, twice the resistor R1 plus R2 times C, which is mostly dominated by R2. That turns out to be about 14 milliseconds. So a very narrow pulse in the microsecond range and then millisecond here. Okay, what's going on over here? This is a monostable. What I've got here is a resistor R3 and then an unknown capacitor C sub X. Depending on the value of the capacitor, we're going to get out a pulse at the output that's going to be related to the value of C. Now the voltage here is going to be almost the power supply, but not exactly. So we're just going to say VCC here, but this output here, I really need to be as precise as possible. So let's put a Zener diode here. This is about 13.3 volts, and this is an 8.2 Zener. That would be about 5.1 volts. So if I pick about 120 ohm resistor, I'll get about 43 milliamps of current going into the Zener, which will get us way out into the Zener region, again, bigger than its minimum current. And then we're going to use a DC voltmeter to measure the average voltage here. I'll talk about this in a little bit. So if we get a pulse like this, it's going to trigger an output pulse of the monostable, and that's going to be equal to the natural log of 3 times R3 C sub X, but where C sub X is the unknown capacitance. Now, what's the average value of this waveform? Well, it's going to repeat itself based on the triggering of our signal. And so the DC value is the integral of our voltage over a period. For this part of the period, it's equal to 0. For this part of the period, the area underneath the curve is going to be the base times the height. So the height here is going to be my Zener voltage. And then the width of this is 1.098 R3 C sub X. And we're going to divide by the period. The period is equal to the natural log of 2 times the quantity 2R1 plus R2 times C sub 1, put that right over here for T. Here's my V sub Z, and here's my 1.098 value and my value of R3. Put all that together times C sub X. Now if I were to vary the resistor R3 such that this equaled 10 to the 6th, then when I had 1 volt out, that would be corresponding to 1 microfarad of capacitance. Take a look at the SPICE simulation of this. Again, I have an oscillator, so I want to have my power supply delayed by a little bit. Delayed it here by 21 microseconds, and I'm going to go from 0 to 12 volts. Now the resistor R3 I calculated to be 1.56K, but I actually adjusted the value with multiple simulations until the output voltage turned out to be the capacitance times 1 million. Here I got a 4.7 microfarad capacitor. That would correspond to an average voltage of 4.7 volts. Consider that to be my calibration circuit. So if we were to build this in lab, I would likewise put a pot there, and then taking a known capacitor, I would then adjust that pot until I got the right DC voltage. So you can see my pulse here, very narrow, triggering a response from the monostable. And then I took the average value of V sub 8 and did this in steady state, and starting from here, taking 1 period each time, I get the same value, and that's going to be 4.7 volts. I went back and I ran other values of C sub X, and so when I put a 2.2 microfarad into that same simulation, I got 2.2043 volts out, so that would correspond to, again, 1 million times this, roughly. When I made the capacitor 1 microfarad, I got 1.0156, and then 0.68, I got 0.6907. What you can see here is that the error is actually growing as my pulse width out is getting smaller. And the reason for that is we're getting into the errors of the chip itself. And this is a capacitance meter using a 555 timer. This next application is making a set of delay wipers using a 555 timer. You can see here I've got an A-stable again. And so I've got a very small resistor compared to here. So I have a very short pulse compared to the total resistance times the capacitance. Let's see if we can calculate what we've got here with the range of the pot and kind of figure out what's going on at the output. Take this RC product, you get about 0.52 seconds, so about half a second. And then if you take a look at the interval here, which is going to be natural log of 3 times the sum of these resistances times the capacitance, depending on the value of R here going from 0 to 500K, we have from 2.31 seconds to about 30 seconds. And then the next time it happens, it'll be a little bit shorter because you get the natural log of 2 instead of the natural log of 3. So we're looking at 1.5 seconds to about 18 seconds. So a fairly long interval of time, and then a short one, and then so on. What happens with the output here? Well, the output's going to be high or low. When the output's high, the voltage is big enough that we can't forward bias this junction, and so we don't get any current flowing. And that's going to cut off this transistor, which is also going to cut off this transistor, and now there's no current for the motor, so the motor is off. Okay, now when the output goes low, current can come in here, we can saturate this transistor, and then provide a current in here to saturate this transistor, and now we've got most of the battery across the motor, and so the motor will move for about a half a second. Now what this is going to do is it's going to wipe the windshield once, and there's a spring that pulls it back. So we'll get one wipe every 1.5 to about 18 seconds. A couple things here. There's a diode here, and as we'd seen in 303 lab, that when you have an inductor or inductive load and you open and close a switch, that energy that's stored in here wants to go into the transistor when it's cut off and basically hit its breakdown voltage. By giving it a path for current to flow, then it can dump that load into the diode. There's also a diode over here, and part of the reason is that when you're switching an inductive load, sometimes the inductor can pull current and make this node go negative, and the base emitter of a transistor actually breaks down at a couple volts. And if current were pulled back through here, then this point would be no more negative than one diode drop. In other words, minus 0.7. Next, I simulated this. I had to take a rough guess for the motor. I didn't have many data on it. I was guessing that it had about a 10 ohm resistance and 100 millihenries of inductance. But just having some inductance here, I'll get that inductive effect in the simulation. I also ran into convergence problems. They had to change ITL4 again from the default of 10 to 100. You can see here for the different values of my resistor, what you call R delay. Started out with here as being 500K. Getting these pulses at the output. And then the current that's going in the motor, you can see getting a shot. Ran the simulation again at 100K for the delay resistor, which is R sub 2B. We have a shorter wait time between pulses, so we're going to do one wipe, and then we're going to do another wipe, and so we can keep adjusting that. So we bring that down to 50K. We're wiping more frequently. And this is some SPICE simulations of the 555 timer and some applications.